Why have we never detected the graviton, the quantum particle of gravity that should hold reality together? We can map black holes and measure quantum fields with absurd precision, yet the graviton remains a ghost. Today we attempt four impossible experiments to detect it. First, we try to measure a single particle and hit the Planck barrier. Then we try to create one, and the machine expands to interstellar scale. Next, we hunt for signals from the sun, only to get buried under neutrino noise. Finally, we try to convert gravity into light, and the vacuum itself fights back. If every door is locked, are we missing the evidence, or using the wrong key? And when we try to force the answer out of nature, every door seems to lock itself. For the past century, physics has been operating under a fractured reality. We possess two master theories that describe the universe with terrifying precision, yet they refuse to speak the same language. On one side, we have the standard model of particle physics, the most successful theory in human history. It describes the subatomic world as a bustling exchange of discrete packets. The photon carries electromagnetism, gluons carry the strong force, and W and Z bosons carry the weak force. For three of the four fundamental forces, the standard model gives us a working, testable description. But then, there is gravity. According to Albert Einstein's General Relativity, gravity is not a particle exchange, but a geometry, a smooth, continuous curvature of the space-time fabric itself. This creates a profound contradiction. How can the universe be fundamentally smooth and fundamentally pixelated at the same time? To unify these two warring descriptions into a theory of everything. Physicists believe gravity must also be quantized. It must be broken down into discrete chunks. It must have a particle. We call this hypothetical particle the graviton. If the graviton exists, it would bridge the gap explaining everything from the dawn of the Big Bang to the hearts of black holes. If it doesn't, our understanding of the universe at its deepest level is fundamentally flawed. But finding it has proven to be an investigation against the universe's hardest limits. Unlike the photon, which we can generate with a simple light bulb, the graviton is painfully elusive. Mathematics suggests it is a massless spin-2 boson, but mathematics can only take us so far. When we try to force gravity into the quantum equations that work for other forces, the math breaks down, spiraling into infinite loops that make no physical sense. We can no longer rely on equations alone. To solve this case, we need hard evidence. We need to drag the graviton out of the theoretical shadows and into the light of a laboratory. And the most logical place to start is to use the most sensitive ruler ever built by human hands. Our first attempt to capture a graviton relies on a technology we know works: the Laser Interferometer Gravitational Wave Observatory, or LIGO. In 2015, LIGO made history by detecting the ripples in spacetime caused by merging black holes. It did this by splitting a laser beam, sending it down two perpendicular 4-kilometer arms, reflecting it off mirrors and looking for a shift in the interference pattern. That shift was smaller than the width of a proton, proving that spacetime is dynamic. But LIGO detects gravitational waves, classical ripples in spacetime, that in a quantum description would correspond to an enormous number of coherent gravitons. Detecting a single graviton is a different beast entirely. It is the difference between noticing a tidal wave hitting the shore and detecting the impact of a single molecule of water. To resolve a single quantum of gravity, we need to dramatically increase the resolution. If gravity is quantized, then at some scale, even a smooth wave should have an underlying quantum structure, individual quanta, that are normally impossible to resolve. To see the graininess of spacetime, our detector would need to sense length changes on the scale of the Planck length, about 1.6 times 10 to the minus 35 meters. That would require upgrading LIGO sensitivity by a factor of roughly 10 to the 36th. It sounds like an engineering challenge, but the real problem is deeper. At this level of precision, quantum mechanics stops being background noise and becomes the dominant force. We would have to look closer than anyone has ever looked before. But precision has a price, and quantum mechanics always sends the bill. The bill arrives in the form of the Heisenberg uncertainty principle. This fundamental law dictates that you cannot know pairs of physical properties like position and momentum with infinite precision simultaneously. The more precisely you try to pin down the position of the mirror to catch a graviton, the more uncertain its momentum becomes. This is not just a measurement error, it is a physical agitation. To measure the mirror's position to within a Planck length, we must bounce high-frequency photons off it. These photons carry immense energy. When they strike the mirror to measure it, they kick it, imparting a random momentum that blurs the very position we are trying to read. This is the back reaction of measurement. To counteract this quantum jitter, we have a solution derived from the early arguments of Niels Bohr and later revisited in the context of gravity by Freeman Dyson, and analyzed in detail by Tony Rothman and Stephen Bown. We must make the mirror heavier. A more massive mirror resists the kick of the photon, reducing the recoil and allowing for a sharper measurement. To achieve the precision required to see a single graviton, the math demands we increase the mass of the mirror substantially. We add layer after layer of shielding, increasing density to pin space-time down. To beat recoil, we make the mirror heavier, until heavier becomes catastrophic. Here, the investigation hits a wall that no amount of engineering can bypass. As we pack more mass into the mirror to stabilize it against the quantum kick, we run into the Schwarzschild radius, the point where a given mass is compressed into a region small enough to form an event horizon. To measure a distance as small as the Planck length, the energy concentrated in the detector's mirror must be so high and the volume so small that the mirror's own gravity takes over. Before we can complete the measurement, the mirror collapses under its own weight. An event horizon forms around the apparatus, trapping the information we sought to extract. The detector doesn't just fail, it becomes causally disconnected from the outside world. According to Stephen Hawking's theory of black hole evaporation, this microscopic black hole would be unstable. It would decay almost instantly, releasing all its mass energy in a brief, blinding flash of particles. We wouldn't get data points, we would get a thermal burst. This leads to a chilling realization: the barrier isn't technological, it's built into the rules themselves. At Planck scales, gravity, quantum uncertainty, and collapse begin to overlap in a way that blocks direct observation. Any attempt to peer directly at the pixelated structure of spacetime triggers a mechanism that destroys the observer's ability to see it. We cannot gently observe the graviton, because at this scale, observation is synonymous with destruction. So we stop trying to see a graviton and try to make one. If the passive approach fails, we switch to an active test. In particle physics, this means brute force. When we wanted to find the Higgs boson, we didn't wait for one to float by. We built the Large Hadron Collider. The LHC smashed protons together at nearly the speed of light, created rare particles for a fraction of a second, and then reconstructed them from their decay. We can apply the same logic to gravity. If nature won't show us a graviton, we'll try to produce one. The plan is straightforward: collide particles with enough kinetic energy to excite the gravitational field, popping a graviton into existence. But this plan immediately runs aground on the rocks of the hierarchy problem. Gravity is the weakest of the four fundamental forces by a staggering margin, roughly 10 to the 36th to 10 to the 40th times, weaker than electromagnetism, depending on how you measure it. To visualize this weakness, consider a simple fridge magnet. That tiny piece of iron can pick up a paperclip, effortlessly overcoming the gravitational pull of the entire planet Earth. The electric force of the magnet wins against the gravitational force of a trillion-ton rock. Because gravity is so weak, the probability of creating a graviton in a standard collision, its cross-section, is vanishingly small. At LHC energies, we produce billions of photons and gluons, while any graviton emission would be far too weak to isolate or detect. To have a fighting chance of creating one, we need to bridge the energy gap. We need to push our collisions toward the energy scale where gravity becomes as strong as the other forces. We need to reach the Planck-energy 1.2, 2 times 10 to the 19th GeV. If the Higgs discovery required a 27-kilometer ring beneath Geneva, what does quantum gravity demand? To answer that, we look at the standard blueprint for a particle accelerator. The maximum energy E that a synchrotron can reach depends on two things: the strength of the magnetic field B used to steer the particles and the radius of the ring R. The relationship is linear. P is approximately equal to 0.3 times B times R. To get more energy, you either need stronger magnets or a bigger ring. Currently, our best superconducting magnets operate at around 8 to 16 Tesla. If we stick with this technology and aim for the Planck energy required to wake up the graviton, we can solve for the radius. The result is not measured in kilometers, it is measured in light years. To build a Planck-scale collider, let's call it a Planckatron, we would need a ring with a circumference roughly the size of the Oort Cloud, the icy graveyard of comets that surrounds our solar system. The machine would be an interstellar megastructure with a diameter of several light years. The engineering logistics of such a device venture into the realm of horror. The structure would require more raw material than exists in the entire Earth. It would need to be perfectly aligned across a void where space itself is warped by the gravity of passing stars. But the true horror is the operational latency. Imagine the control room on Earth. You send a signal to the superconducting magnets to initiate the beam. That signal travels at the speed of light, taking months or years to reach the far side of the ring. That signal travels at the speed of light, taking years to reach the far side of the ring. The physicists who designed the experiment would be long dead before the first collision data arrived. It is a machine that operates on the timescale of civilizations, not human careers. It is an engineering purgatory where the feedback loop is severed by the vastness of space itself. At this scale, physics isn't limited by ideas, it's limited by civilizations. This thought experiment reveals that detecting the graviton via high-energy collision is not strictly forbidden by the laws of physics, unlike the black hole collapse in Chapter 1, but it is economically and energetically impossible for us. Russian astronomer Nikolai Kardashev classified civilizations by their energy consumption. A Type 1 civilization controls the energy of its planet. A Type 2 controls the energy of its star. We are currently a Type 0.7 civilization. To power the Oort Collider and concentrate Planck-scale energy into a single point would require an energy budget that exceeds the total output of our entire technological species. We are trying to buy a skyscraper with pocket change. Unless we discover a new physics that allows for radically stronger magnetic fields or linear acceleration methods we haven't dreamt of, the brute force path is closed. We cannot afford the entry price to the Planck realm, but if we cannot build the source, perhaps we can steal the signal. We don't need to build a stellar reactor, we're already orbiting one. If we can't build the source, we'll steal the signal from nature's own reactor, the sun. Since we lack the civilization-scale budget to build a generator, we switch to a passive search. We need to intercept a source of gravitons that is already broadcasting. Fortunately, we live in the orbit of a giant unshielded nuclear reactor, the sun. Deep in the solar core, amidst the chaotic fusion of hydrogen into helium, particles are constantly scattering. In the sweltering plasma, electrons and ions collide with furious kinetic energy, while these collisions primarily produce photons or light and neutrinos. Theoretical estimates suggest that thermal interactions should also radiate extremely weak quanta of gravity. The flux could be enormous. Order of magnitude estimates put the sun's graviton emission at around 10 to the 24th per second. These particles stream out from the core, passing through the sun's outer layers and flooding the solar system. We are currently bathing in a rain of solar gravitons. To catch them, we need a detector with massive stopping power. A tabletop sensor is useless. The particles would pass right through it without leaving a trace. We need a target mass of planetary proportions. In this solar spycraft scenario, we could use the Earth itself, or perhaps Jupiter, as part of the detector. The concept is to use the bulk of the planet to increase the probability of a graviton collision, hoping for any rare interaction that could leave a detectable signature, most plausibly through graviton-photon conversion in strong fields. In principle, a planet could help suppress some backgrounds from one direction, but it wouldn't solve the fundamental problem gravitons and neutrinos both pass through almost everything. We have the source, we have the shield, we have the math. But in particle astronomy, the hardest part isn't finding a signal, it's surviving the noise. The problem is that the sun is a messy broadcaster. It doesn't just emit gravitons, it screams neutrinos. Neutrinos are the famous ghost particles of physics. They are electrically neutral and barely interact with matter, allowing them to pass through light years of lead with an extremely low chance of interaction. For decades, they were the hardest things to detect in the universe. But compared to the graviton, the neutrino is a brick wall. The interaction strength or cross-section of a neutrino is governed by the weak force. The interaction strength of a graviton is governed by gravity. The gap between them is roughly 34 orders of magnitude. That means for every single graviton event our planetary detector might catch, it gets bombarded by 10 to the 34th neutrinos. This creates a neutrino floor, an irreducible background of noise that no amount of shielding can block. Because neutrinos and gravitons are both penetrating particles, anything dense enough to block the neutrinos to clean up the signal would also block the gravitons. We cannot filter the noise without destroying the music. To visualize this hopelessness, imagine standing in the middle of a football stadium during the Super Bowl. The crowd is roaring so loudly you can't hear your own thoughts. That roar represents the neutrino flux. Your mission is to detect the sound of a single pin dropping on the grass field. That pin drop is the graviton. You are not deaf. The signal is physically there, but it is statistically annihilated by the environment. Physicists Tony Rothman and Stephen Bound crunched the numbers on this nightmare scenario. They calculated that if we built a detector the size of Jupiter and placed it in close orbit around a neutron star, a much more intense source of gravitons than the Sun, and if we somehow made the detector 100% efficient, we might detect one graviton every decade. But in that same decade, the detector would register countless neutrino events. Distinguishing that one gravitational click from the octillions of neutrino clicks is statistically impossible. The data is effectively encrypted by entropy. The signal is lost in the ocean of noise. Once again, the direct path is blocked. We can't see them because of the Planck barrier. We can't make them because of the energy gap. We can't hear them because of the noise problem. We are running out of options. We need to stop playing by the standard rules of particle detection. We need to change the nature of the particle itself. So we try the oldest trick in experimental physics: don't detect the thing, convert it. We have failed to catch the graviton in its natural habitat. We have failed to produce it on demand. We have failed to eavesdrop on its whispers. It seems the particle itself is incompatible with our detectors. So we attempt one final strategy. Instead of detecting the graviton directly, we try to convert its signature into something we can measure. In 1962, the Soviet physicist M.E. Gertzenstein proposed a mechanism that sounds almost too convenient. He proposed that in an extremely strong magnetic field, gravitational waves could mix with electromagnetic waves, allowing an ultra-rare graviton-photon conversion. Conversely, a photon can transform into a graviton. This is the Gertzenstein effect. The physics behind this is elegant because gravity couples to all forms of energy, and a magnetic field contains energy the two fields can mix. If we shoot a graviton through a powerful magnet, the oscillation of the gravitational wave, the two fields can couple, allowing a tiny fraction of gravitational energy to convert into an electromagnetic signal. This changes the entire game. We don't need to build a detector for the elusive graviton anymore. We just need to build a standard photon detector, a technology we mastered a century ago. We essentially build a graviton-to-light converter. We point a long vacuum-sealed tube at a source of gravitons, wrap the tube in massive superconducting magnets, and look for an impossibly faint excess of photons light that should not be there. The plan is perfect on paper. But to make it work, we need a magnetic field strong enough to push the vacuum into a nonlinear regime. To get a conversion rate that produces even a single photon within a human lifetime, the magnetic field has to be astronomically strong. We're not talking about the magnets in an MRI machine, which are around 1.5 Tesla, or even the monster magnets at the LHC, which reach about 8 to 16 Tesla. We need magnetic fields that push into the range of 10 to the 13th Gauss, or higher. When we push into this regime, we hit the QED critical field, often discussed through the Schwinger limit. In classical physics, a vacuum is just empty space, a void where nothing happens. But in quantum electrodynamics, or QED, the vacuum is a seething ocean of virtual particles. Pairs of electrons and positrons are constantly popping into existence and annihilating each other in timescales too short to measure. They are virtual fluctuations, but a magnetic field represents potential energy. If the field is strong enough, it can rip these virtual pairs apart before they can recombine. It feeds them enough energy to make them real. At around this critical field strength, the vacuum becomes strongly nonlinear, and pair production can no longer be ignored. The empty space inside our detector begins to boil. The magnetic energy spontaneously decays into real matter and antimatter in the form of electron-positron pairs. This phenomenon is called vacuum polarization. The vacuum ceases to be a transparent medium and becomes a nonlinear fluid. It acts like a plasma. The newly created soup of charged particles creates its own internal electromagnetic fields that oppose the external magnet. This is known as screening. The vacuum effectively builds its own shield to dampen the magnetic field we are trying to apply. Worse, this boiling void creates vacuum birefringence. The space itself acts like a prism, bending and distorting any light passing through it. Our converter becomes opaque, the very mechanism we needed to facilitate the transformation. The extreme magnetic field triggers a response from the vacuum that jams the signal. We're trying to detect a faint signal with an amplifier that generates its own noise the moment we turn the gain up. The vacuum isn't empty, it's a medium, and it has limits. We have now exhausted the 4 primary paths of direct detection. When we looked too closely using LIGO, we created a black hole. When we tried to create the particle using a collider, we ran out of energy on a galactic scale. When we listened to nature using the sun, we were drowned out by noise. When we tried to convert it using a magnet, the vacuum turned opaque. This pattern is not a coincidence. It is a dossier of evidence. It suggests that the graviton is sequestered behind a series of fundamental locks: the Schwarzschild radius, the Planck scale, the neutrino floor, and the Schwinger limit. Some physicists argue that these barriers are a cosmic censorship, a hint that perhaps gravity is not meant to be quantized in the same way as other forces. Perhaps spacetime is fundamentally smooth, and the graviton is a fiction of our mathematics. But there is one final possibility, a way to prove the existence of the particle without ever catching it. We don't need to catch the messenger to prove the message was delivered. We just need a trace that cannot exist without it. If direct detection is locked behind nature's barriers, we need a different witness. So is the case closed. Is the graviton nothing more than a theoretical necessity, forever hidden behind the Planck barrier and the Schwinger limit? Not quite. While nature has effectively banned us from seeing the particle face to face, it has left a window open for us to see its shadow. The future of this investigation lies not in building galaxy-sized colliders, but in the delicate silence of quantum information theory. In 2017, 2 groups of physicists proposed a brilliant tabletop experiment known as the BMV experiment, named after Bose-Marletto and Vedral. The logic relies on a fundamental rule of quantum mechanics. A purely classical mediator on its own cannot generate entanglement between 2 isolated quantum systems. Only a quantum mediator can do that. The plan is to take 2 microscopic diamonds, put them into a quantum superposition, where they exist in 2 places at once, and let them interact solely through gravity. If the diamonds become entangled, if measuring one instantly affects the state of the other, then the force connecting them must be quantum. It would prove that gravity is carried by a particle, the graviton, without us ever needing to detect a single one directly. We are shifting our strategy from brute force to subtle inference. We don't need to force a direct detection. We just need to measure a correlation that cannot exist without a quantum gravitational link. The universe has constructed an incredible firewall around its deepest source code. It shields the singular nature of spacetime. With black holes, drowns it in noise, and guards it with boiling vacuums. But these aren't just barriers. They are clues. They tell us that the union of gravity and the quantum realm is the most protected secret in nature. And if the history of science has taught us anything, it's that the harder the universe tries to hide something, the more transformative the truth will be when we finally find the key. If the graviton exists, its evidence is still out there.